Okay.
Okay, I've started recording. It, go ahead.
Uh, Perfect. So I'm Elie Libbos. I work with Dr. Banerjee. He's my advisor, and I work on variable pole induction machines for EVs, which I'm going to talk about today. So currently, permanent magnet motors are dominating the EV industry, with the second most dominant motor being induction machine. Uh, and the reason for that is because of these PM machines have higher power density, higher efficiency compared to other motors. But induction machines are rugged motors that uh, uh, that are less expensive and have advantages in terms of cost. But the current trend, the US Department of Energy, in their 2025 target, they're pushing to decrease the magnet cost as a percentage of the total motor to less than 4%. Which means if we want to meet these targets, we need either to use less magnets or different types of magnets, or use machines which are inherently magnet free, like the induction machine. And this machine has been widely used in the industry. It's a well-established machine, very well known. So here are examples of some modern designs which use the induction machine. Here's the Audi e-tron 2019, which uses two induction machines. And for example, there's Tesla Cybertruck. Actually, Tesla Cybertruck is very interesting. They use two induction machines and one PM motor, and two PM motors and one induction machine in the same car. But let's look at some of the problems with EV motors and what we can do to solve them. And let's look first at fixed pole motor. So these are the conventional motor where you already kind of know the magnetic pole count of the machine once you have it or you design it. So the orange curve shows the ideal torque speed capability for an EV motor. And ideally, we would like to provide a high torque at low speeds below zero point 0.1, but then beyond zero point 0.1, we would like to keep the torque capability can drop, but we would like to maintain a decent amount of cruising torque at zero point 0.2 because we need to overcome basically all the forces dragging us backwards. Otherwise, we cannot cruise at these speeds. But if we look at a fixed pole machine, an induction machine in this case, the torque speed capability beyond zero point 0.1, you see that the torque capability drops well below this orange capability, which we need. And this is one of the biggest challenges in EV application. They're known as wide speed range application. And the reason that happens has nothing to do with the machine itself, but it's more coming from a constraint from the power electronics. So at zero point 0.1, you hit the voltage limit of your power electronics. Basically, you want more voltage out of your machine, but you cannot to operate your machine, but you cannot get more voltage. You hit the limit, and that's basically a voltage limit. And beyond that, you have to reduce the flux in your motor, and basically the capability due to certain non-idealities, it drops rapidly. So a possible solution to this problem is to use a higher rated power electronics converter, like 40% higher rated drive, either higher rated voltage or higher rated current. And you see the orange capability, which is again the ideal capability, and the blue capability is the capability of the motor with a conventional drive, and the yellow capability is once we increase the rating of the drive by 40%. But since EV applications are pushing towards more power density, increasing the power rating of the converter may not be the best solution. And you already have a lot of extra, like the yellow capability is much higher than the orange capability, and you're not using that extra capability. So how do we look at this problem and how do we solve it? So fixed pole machines have this problem. Eventually you'll hit a power electronic limit, voltage limit, and then your torque capability will rapidly drop. So possible solution to solving this problem is using more phases. So typically motors are driven from conventional motors from three-phase converters, and three-phase converters basically they dictate the pole count of the machine. So for example, if you have a stator in your machine and you want to drive it from three-phase, you need technically only three phases coming out of your motor to the power electronics. And once you stack your winding and do your winding design, your magnetic pole count is determined by whatever winding, the way you design your winding on your stator. Now, currently with advancement in power electronics, these higher number of phases are becoming more attractive. So driving the motor from a 9-phase or an 18-phase converter are definitely becoming more researched and more hot areas. But what is the advantage if we drive a machine from an 18-phase converter to a three compared to a 3-phase converter? And this is where the idea of not having a magnet is a huge advantage. So in a permanent magnet motor, you cannot change the pole count on your stator, because if you do so, your rotor magnet already has a pole count which is determined physically from the construction. However, if we look at the induction machine, your rotor has a squirrel cage. It doesn't have any magnet. And this squirrel cage will copy whatever magnetic pattern is coming from the stator. It will induce basically its magnetic pattern based on the stator. So it will happily follow your stator. So what this means basically is when you have more power electronics, basically you're not limited to a pole count because you have control over so many motor current. You can change the pole count of the stator. And once you change your stator, your rotor will follow you because it's an induction machine. And that's the biggest advantage of having induction machines with with power electronics, basically with high number of phases, because you can utilize this property of having a lot of degrees of freedom and flexibility, because an induction machine is not constrained in construction by a magnet. So in addition to changing the magnetic pole count of the motor, we found out that toroidal windings, so kind of like the windings you see on transformers, are better for pole changing application. And the advantage of having these types of winding is also they're exposed for cooling. So they have certain advantages in that area. So now we know that we can change the magnetic pole count of an induction machine. But the next question that obviously comes to mind is, why do we need to change the pole count? What's the benefits of doing so? And how do we solve the challenges in EVs? That's the first thing I'm going to talk about. Then I'm going to show you how we can actually optimize the losses in the machine by using the pole count as a decision variable. And then basically we will look at the experimental setup and the experimental results we have. So I'll talk again about the EV application requirements. We need a high torque until a certain base speed, and beyond that we must be able to cruise at a really high speed with a decent amount of cruising torque. And that's the first major challenge in EV. So it's called wide speed range. But the second challenge is that your EV motor doesn't operate at its rated condition for most of the time. It actually you can drive, like you can accelerate really fast with a high torque, you can go really high speed and cruise on a highway, you can be stuck in traffic where you're accelerating with low torque. So there's all sorts of driving behaviors and different drive cycles. So your motor must not only be efficient at the rated condition. Actually, rated efficiency doesn't tell us much, and peak efficiency, and unless we're studying the thermals. But from how much energy we're going to draw from the battery, it matters how efficient your motor is under different conditions. And it's very important to be able to optimize the losses, not just at one design point, but at several operating conditions. So let's tackle the first problem first with variable pole. How do we improve the speed range? How do we overcome that challenge? Because we saw that if we want to use a fixed pole machine, we need a higher rating converter to overcome the limitations at high speed. Or we need basically, there is another way to improve it, which is to minimize the leakage inductance of the machine, which I didn't go through in details, but it has one of the fundamental disadvantages. It has lots of trade-off with losses. So minimizing the leakage, and there's not much you can get out of it. So let's look at the third type of solution, which is the variable pole solution. So once we look at, so assume here you have a motor, which is a 6-pole motor. Somebody gave me a 6-pole motor as a black box. I took the winding out of that motor, removed the 3-phase converter, and drove it from a 18-phase converter. Let's say I did that, and I didn't change anything physically in the motor. So the design is already there. And let's say I ran this motor at 6-pole. What will happen is you can see the red dashed line below the speed, the base speed omega b Our torque was 1 per unit. We delivered the rated torque, but beyond that point, we hit the inverter voltage limit. So we cannot get more voltage out of the machine power electronics, basically. And then our torque capability rapidly drops, the red curve. So now one class of solution is again to use higher rated power electronics and to do to optimize leakage. But another solution is just since I have now an 18-phase converter, I can control my PWMs and just change the magnetic pole counts on the stator. Rotor will follow because it's an induction machine. So you see, exactly after point one, switching from a 6-pole to a 4-pole improves the torque capability, and above point two, switching to a 2-pole improves the torque capability. So as you go to higher speeds, you can switch to lower pole count and improve your high speed torque capability. So that's a huge advantage. So you don't need to take care of it at all at a design stage. You don't need to do any design sacrifice. Just control your power electronics converter to change the pole count on the fly, and you will be able to overcome all of these high speed challenges and maintain a decent amount of cruising torque. Uh, so this property of induction machines being able to maintain a wide speed range has been shown in the literature. Variable pole induction machines maintain a wide speed range, but one of the things that's always been linked to this machine is that they always look at it from a speed perspective. Like if you have a speed below point 0.1, use a 6-pole. If your speed is below point 0.1, point 0.2, use a 4-pole. If your speed is higher than point 0.2, use a 2-pole. But what about torque? Torque also plays a role, right? Because now we're looking at it from a single variable perspective, only speed. So let me illustrate this. Let's look at the low speed. If the speed is below point 0.1, if we go to the literature, what we will see is we will be choosing a 6-pole irrespective of the torque because it has the highest capability. But in EVs, we're not going to always drive near the rated torque. So if we look at 2 points, A and B, at point A, if I want to select my pole count, it's very easy because only 6-pole can provide me that torque. So at point A, I don't have much of a choice. But if we look at point B, we don't need much torque. Now all of them, 2, 4, and 6-pole can produce the torque. So now the pole count is a degree of freedom. I can select which pole count is more efficient in this operating region rather than just sticking to one single pole count. So, so let's look at how do we minimize the losses using the machine pole count. So first, I'm going to spend a bit of time on the electromagnetics of the problem and what's really happening. So if we look at this, a 6-pole, again, the motor is a 6-pole nominal motor. We have roughly an air gap flux density of 0.75 Tesla, and the material is close to its limits, which is 1.7 Tesla. It's an M1924 material. So, uh, so at 6-pole, we're close to the limits on the yoke and on the teeth. But now if we take that same motor and change its configuration from a 6 to a 4-pole, you will see that the limits that come on your flux density are not, it's no longer the teeth are limiting you. It's now the yoke of the machine. It's roughly at 1.7 Tesla. And you can only draw 0.65. As you go to 2-pole, you can only draw 0.35 Tesla, but now your yoke is saturating a lot. Now, this obviously doesn't mean at a design stage if a 2-pole cannot reach the same flux density at 6, because you'll always design your motor, a 2-pole motor differently than a 6-pole motor. But what it says is given a 6-pole, if I have a 6-pole motor, I can only push partial flux density in lower pole count. But this is good because lower pole counts are going to be used only at high speed. We don't really need them to deliver the full torque. We only need them to overcome the drop in torque at really high speeds. So we don't really need full flux density. So we don't even need to alter that 6-pole motor design to accommodate for these lower poles. Now, if we go higher in poles, you can get slight increase in flux density up until 8-pole. But beyond that, you cannot get really a lot of flux density. This is mainly because your teeth now are at their limit. So no matter how much you try to push flux density, your teeth are at their limit. So probably for this motor, we'll use it from 2 up until 8-pole. And beyond that is not really much. There's not really much benefit in changing the pole beyond that. But if we look again at the 6-pole, 4-pole, 2-pole compare, if we look only at this image, this kind of tells us that 6-pole can can have more flux density. So it's kind of in the air gap. So it's kind of better, but this doesn't tell us the full story, because when we run with a torque that's not our rated torque, we don't want full torque, we're not going to use the full flux density. So the question that comes to mind, is it better to decrease my flux density in 6-pole or just use these lower uh, flux densities available for me in 4-pole and 2-pole? And this question is answered by looking at the no load current, which is kind of known as the magnetizing current in an induction motor. And typically that current is not very important at really high torque because it's a small proportion of the full load current. But when you're operating at a low torque, it could be close to it could be of the order of your full load current. So it's very important to minimize it. And you can see that as you go higher and higher in pole count, if you look in the stator slots, your no load current is increasing significantly. And now let's take a look at one case where you have 8-pole and 10-pole. Both of them have the exact same air gap flux density, but the no load current is significantly higher in 10-pole. So this current increases very rapidly with pole count. And what does this tell you? This tells you that lower pole counts for the same flux density, they will be they can produce their torque with a smaller no load current, and they're like more effective in producing their torque with they're more effective at producing their torque with smaller flux densities. However, they're limited to a certain flux density, so it's kind of a trade-off in here. There's kind of an interesting trade-off that emerges. So if we look at, for example, a particular speed, let's say we're looking here at stall, the motor is at 0 speed, we're accelerating, and we draw power losses versus torque. We can see clearly that we draw for different pole count. 8-pole has the highest torque capability. But if you go down and down, you don't need really a lot of torque, then it's not very efficient. Then 6-pole becomes more efficient in this region, less losses. And basically 4-poles becomes more efficient in this region and 2-pole becomes more efficient in this region. So previously we have in the literature they have shown, and I've shown in this presentation, that we can improve the speed range of the machine by going to lower pole at higher speed. But in here what this graph tells us is we can also use it even at the same speed. If we can use pole, we can switch to lower and lower pole count as we need less torque to reduce the losses in the machine, so we can optimize the losses. And we took this example, and now currently we are working on a design of an actual 157 kilowatt motor, and we want to compare it with we want to compare two motors, one that's fixed pole designed with a higher rated drive and everything, compared to a variable pole. We want to compare them in terms of efficiency maps. And you can see in here that the fixed pole motor only reaches 96% of efficiency, but the variable pole motor at high speeds reaches 97 and 98%, and even has a much wider 96% efficiency region. Meaning this motor is much more efficient because basically it's not just improving our speed range, it's much more efficient at high speed and low torque. So overall, once we go to the next step, what we would like to look at is actual driving scenarios and how much energy we can save in realistic scenarios by comparing the two motors. So now I'm going to talk about the experimental setup we have in the lab and the experimental results. So we have a machine which Dr. Matt McGill built when he was doing his PhD thesis in here. So it's a 36 slot. It's an induction machine with toroidal winding, and it has 36 slots. And what's very interesting is you don't have access to only 3 terminals. You have access to each of the individual 36 slots of the motor. Meaning you can even drive all 36 separately. You can connect them in series and parallel and then drive them from a 3-phase converter. Or what we did in here is we built 2 9-phase converters, they're identical converters, and we drive basically 18 terminals of the machine. And we built a controller board which basically sends the PWMs and takes care of the current feedbacks to drive this motor. And the interesting thing is you don't change anything physically when you change the pole count. It's only in the phase it's encoded in the phases of the PWM. Everything like the pole count of the machine is encoded in at this stage of the PWM. So in here, what we did is we did a test where we looked at step sizes of 400 RPM, and we tested from 100 to 3,300 RPM this motor. And we tried to generate color maps. So the color indicates, so if the color is yellow, this indicates that the 6-pole is the most efficient in here. If the color is green, it's 4-pole, and blue, it's 2-pole. And you can see it's something very interesting, that 6-pole is the most efficient only at high torque. So it's even at low speeds, I would prefer to use a 4-pole or a 2-pole at lighter torques because they're much more efficient. Just like we predicted in the theory, they're going to be much more efficient than this 6-pole motor at light loads. And there are several reasons why they'll be more efficient at light load and high speed, including the lower magnetizing current, which we talked about. Also they're running at a lower fundamental frequency, so lower core losses in the machine, lower skin effect when we go to really high speed designs. They have lower skin effect, and so on. So in here, I'm showing you a graph of the experimental power loss at 900 RPM versus torque for the when we run the motor at 6-pole, 4-pole, and 2-pole. And you see that when we run the motor, so first of all, at this speed, only like 6-pole has the highest torque capability. Basically, we determine highest torque capability. We look at, for example, the 6-pole graph, and it's the highest point on the right we were able to reach in terms of without violating basically the limits of current limit of the machine. And then you can see in here, um, it's basically 4-pole has lower torque capability and 2-pole has lower, because this is a low speed operation. And this machine was designed at 6-pole. But once you see that below point B, actually, if you don't want to use 6-pole because it's not very, so if we take this 6-pole motor, we don't want to actually use 6-pole below point B because it's not very efficient. 4-pole is more efficient, and below point A, 2-pole is more efficient. So roughly we could cut down the losses, like in here, for example, from 100 to 50 watts. So that's a significant decrease in losses. We can do just by using lower pole counts, since they're more efficient at producing light loads. Now, even more, we can use this pole changing capability not only to optimize losses. For example, optimizing the machine losses doesn't necessarily lead to the best system performance. For example, another strategy is to minimize the machine current. And if we minimize the machine current, we can minimize the power that's being processed by the power electronics. And that can lead probably to a more efficient power electronics operation. And we can always combine all of these losses and build an objective system for the entire drivetrain and see. So it's not only going to impact the motor losses. And in here we plot the torque per unit of current. So it's torque per amp. And you can see that 6-pole below point D. So if the torque is really low, we get more torque out of a current by using a 4-pole. So basically this can be said in another way. So below point D, 4-pole has needs less current for the same torque compared to 6-pole. And below point C, 2-pole needs less current. So as we go lower in torque, again, a similar pattern. We can use much less current to produce the same torque in the machine. Now, once we go to 1,700 RPM, for example, this is this speed in here, for example. And in here, you can see that 6-pole no longer, although this is a 6-pole machine, since this is a high speed for 6-pole, for this machine, it no longer has the highest torque capability. It is roughly like 1.2 Newton meter, but 2-pole can allow us to get 1.4, roughly 1.45 Newton meter of torque. And not only that, not only did 2-pole give us more torque capability, but basically because of the higher core loss, more skin effect on 6-pole, because it's running at a higher frequency, and because leakage, which something which we usually ignore analytically, but plays a very important role at this high speed. Basically, 6-pole is very inefficient. Even not only 2-pole improved our torque capability, but it also provided us with much less losses. It produced the torque roughly, if we look at, so we were able to produce at most 1.2 Newton meter with six pole with a 300 watts of losses. But with two pole, if we change the pole of the motor simply at this high speed, we can draw up to 1.4, 1.5 Newton meter of torque with roughly 170, 175 watts of losses. So much less losses, more torque out of the machine. So in conclusion, the variable pole induction machine can meet the torque speed capability of requirement of EVs. And here's, for example, a graph for the machine, the 157 kilowatt machine we are working on. This is an analytical graph, but you can see for the orange capability, it's the ideal capability. We can meet, so we designed a six pole motor, but we can easily meet it with variable pole operation. But if you look only at six pole operation, if we kept that motor and ran it as a fixed pole motor, it would have never met that orange capability. So we were able to meet that through power electronics control. And these motors have a better efficiency. They run at higher speeds with more efficiency compared to fixed pole induction machines. And they can have a better partial loading efficiency when you're not driving for the full torque. So they can have a better efficiency. And this will tend to also affect the system, right? So we have now much less losses, much less current being processed by the power electronics. So this will propagate throughout throughout the system. And the interesting thing about these high number of phases is we're dividing basically the same power that's being processed by the power electronics over more phases. So we can shrink the size of each phase and probably think about integrating physically the motor and power electronics into one package, which is really challenging, but it's one thing that's being looked at a lot in currently in research. And with the higher number of phases, basically nature of these converter offers basically an advantage for this integration. Uh, I would like to thank Poets for funding the project and the Granger Center. Thank you, and I'm open for question now. So, does anybody have any questions? Um, okay, so if there's no questions, yes, probably.
Very nice.
Thank you. Okay, I don't think there is another presenter today, so should we? All right. Right, thanks.